Every day you use things that feel ordinary. Your phone, your internet connection, electricity flowing through your house. They work so reliably that most people never question them. But if you dig deeper, many of these technologies run on principles that scientists don't completely understand. The systems function, the equations work, yet the full explanation remains incomplete. These are 20 things we use daily that don't fully make sense. Electricity powers almost everything in modern life. Lights turn on instantly, devices charge, motors spin. But electricity isn't a physical substance flowing through wires. It's the movement of electrons interacting through electromagnetic fields described by electromagnetism. The equations predict behavior perfectly, but the deeper nature of electric charge is still not fully understood. Wi-Fi signals your internet connection travels through invisible radio waves bouncing around your home. Walls reflect them, metal blocks them, devices interfere with them. Yet somehow your laptop reconstructs the signal and turns it back into videos, messages, and websites. A chaotic cloud of signals becomes clean information. Touchscreens, every time you tap your phone screen, it detects your finger instantly. Most modern phones use capacitive sensing to measure tiny electrical changes caused by your skin. The screen detects a disturbance in an electric field and calculates your finger's position. You're not actually pressing a button, you're disturbing an invisible electrical map. GPS navigation, your phone knows your location within meters. It does this by measuring signals from satellites orbiting Earth. But because those satellites move quickly and experience weaker gravity, time flows differently for them due to general relativity. Without constant relativistic corrections, GPS would fail. Your directions only work because engineers adjust for time distortion in space. Batteries, power, phones, cars, and laptops. Chemical reactions inside them move electrons through a circuit, creating usable energy. But predicting exactly how certain battery materials behave at the atomic level remains extremely difficult. Scientists can build them, but the microscopic chemistry is still being explored. Artificial intelligence, AI systems, can translate languages, recognize faces, and write complex text. These systems are built from neural networks inspired by the human brain. Yet, when an AI produces a decision, researchers often cannot fully explain how the internal calculations produced that result. The system works, but its reasoning can remain hidden. The internet connects billions of devices worldwide. Data is broken into packets, routed through thousands of independent networks, and reassembled instantly. No single system controls the entire network, yet the global structure functions reliably. Most of the time, a decentralized system operating on trust, cooperation, and constant adaptation. Your refrigerator removes heat from food and releases it into the room. This process relies on a cycle of compression, expansion, and evaporation of a coolant. The thermodynamics are well described by thermodynamics, but the microscopic behavior of heat transfer in complex materials remains incredibly difficult to model perfectly. Voice recognition. Devices can understand spoken commands and convert speech into text. Human language contains accents, tone shifts, and background noise, yet software can interpret it quickly. Machine learning systems analyze patterns in massive datasets to recognize speech, but even engineers sometimes struggle to explain exactly why certain models work better than others. Vaccines train the immune system to recognize threats before real infection occurs. A weakened or inactive version of a virus prepares the body to respond faster later. The immune system builds long-term memory cells that stay ready for future attacks. The result is powerful protection created from a tiny preview of the threat. Search engines, typing a few words into a search bar, instantly produces millions of organized results. Search engines analyze hundreds of ranking signals. They evaluate links, content, relevance, and user behavior. Even experts inside the industry cannot fully predict exactly how the algorithm will rank every page. Digital encryption. Modern communication relies on encryption. Mathematical algorithms scramble information so only the intended receiver can read it. These systems depend on extremely difficult problems like large number factorization. They protect banking, messaging, and online identity. Yet their long-term security depends on assumptions about future computing power. Glass looks solid, but its internal structure behaves more like a very slow-moving liquid. Atoms inside glass lack the ordered crystal structure of most solids. This unusual structure explains its transparency and fragility, a material we see every day that behaves differently from most matter. Microwave ovens. Microwaves heat food by vibrating water molecules using electromagnetic radiation. The molecules spin and collide, creating heat. But predicting exactly how microwaves distribute energy inside irregular foods is surprisingly complex. That's why food sometimes heats unevenly. Cloud storage. Photos, videos, and files appear instantly across devices. But the cloud is really a massive network of data centers filled with servers. Files are copied, distributed, and backed up across multiple locations. A global storage system working constantly behind the scenes. Credit card systems, a single tap of a card triggers communication between multiple financial networks. Verification, fraud checks, and authorization happen in seconds. Thousands of systems coordinate to approve or deny a transaction, a complex financial machine working invisibly behind a simple payment. Navigation maps, digital maps, constantly update traffic, construction, and road closures. This happens by analyzing data from millions of devices moving through cities. Your phone becomes part of a massive real-time sensor network. Each driver contributes tiny pieces of information that guide everyone else. Streaming video, movies stream smoothly even when internet speeds fluctuate. Streaming platforms compress video into small packets and adjust quality automatically. The system predicts how much data your connection can handle, a constant balancing act between speed, compression, and quality. Digital cameras. Modern cameras convert light into electrical signals using image sensors. Millions of tiny pixels capture brightness and color information. Software then reconstructs the image using complex algorithms. The final photo is a combination of physics, electronics, and computational processing. The human brain, the device you use most every day, is your brain. Billions of neurons send electrical signals across trillions of connections. From that activity emerges thought, memory, emotion, and awareness. Science can measure brain activity, but how physical signals create subjective experience remains one of the biggest unanswered questions in science. Modern life runs on systems we trust every day. Electricity, networks, navigation, communication, they work so well that most people never question them. But behind their reliability lies something surprising. Even in the age of advanced science and technology, many of the tools we depend on are built on ideas we don't completely understand yet. And the deeper we investigate them, the more mysteries we discover.